Now this session, module 2, which is nothing but elastic properties of material, we see the expressions for K in terms of alpha and beta and expression for rigidity modulus in terms of alpha and beta. Now we see the expressions for K in terms of alpha and beta. Consider a unit cube OX is equal to OY is equal to OZ is equal to 1. That means that it is having a unit cube, means dimensions are 1 in all the x-axis, y-axis and z-axis. It is unit. Now let the initial volume of a unit cube be V, which is equal to 1. Since the dimensions are 1, volume also goes to 1. Let Tx, Ty and Tz be the tensile stresses acting along x, y and z axis on a cube. What is Tx is the stress along the x-axis and Ty is the stress along the y-axis and Tz is the stress along the z-axis as shown in the figure. You can see the figure diagram over there. Tx, Ty and Tz are mutually perpendicular and the tensile stresses acting along x, y and z axis. Here alpha is the linear strain, elongation per unit length per unit stress along the direction of the force. We have defined what is alpha longitudinal strain coefficient, what is beta lateral strain, which is nothing but lateral strain is nothing but the contraction and alpha is nothing but the elongation. So we know that here alpha is along the direction of the force and beta is along the direction perpendicular to the force. And Tx stress produces an increase in length alpha Tx along the x direction. As we have discussed in the previous sections, x is equal to TL alpha. Since here L is 1, dimensions are 1, so we can take it as x is equal to alpha Tx. Therefore, we have taken Tx stress produces an increase in length of alpha Tx as length is 1. And Ty and Tz are perpendicular to x direction and produces beta Ty and beta Tz along the x-axis. Here you have to remember these two things where Ty and Tz are perpendicular to the x directions. Always beta acts along the direction perpendicular to the force as mentioned here. So beta is in the direction perpendicular to the force, which is nothing but the contraction. So Ty and Tz are the perpendicular into x-axis, produces a contraction beta Ty and beta Tz along the x-axis. Along x-axis, so you are, since length is unity, along x-axis, x direction now becomes increment in the size is 1 is the initial volume, 1 plus alpha Tx, which is because of the produces an increase in the stress alpha Tx, which we have discussed here. Alpha Tx produces, it is an increment along the x direction. Beta Ty and beta Tz are the contraction, therefore we take it as a negative along the x-axis. So 1 plus alpha Tx minus beta Ty minus beta Tz along the x-axis. This is the equation 1. Similarly, we can generate equations along the y and z axis based on the directions of the stresses and contractions produced. Now we can see that along the y axis, the increment in the length will be 1 plus alpha Ty because it is along the y axis minus beta Tz, it is contraction, minus beta Tx along the y axis. Here along y axis, alpha Tx is the stress along the y-axis expansion, beta Tz and beta Tx are mutually perpendicular to y-axis, so we have taken as negative terms here. Similarly, the same concept applies along the z-axis, that is 1 plus alpha Tz minus beta Tx minus beta Ty. Because x and y are perpendicular to z, so therefore x and y directions, they are contractions, so we are getting the equation as 3. So we are x-axis equation 1, y-axis equation 2 and z-axis is equation 3. Now the final volume of the cube, we know that volume of a cube is nothing but a cube. So final volume of the cube is nothing but along the x-axis, along the y-axis and along the z-axis. So equation 1 into equation 2 into equation 3 as the volume of the cube is a cube. So what is the final volume of the cube is nothing but you multiply these three equations and neglecting the higher powers of alpha and beta, take one common in all the three equations. So 1 plus alpha is taken common, tx plus ty plus tz minus 2 beta into tx plus ty plus tz. We are neglecting the higher powers of alpha and beta. Rearranging the terms, we are getting as final volume of the cube as 1 plus alpha plus 2 beta, alpha minus 2 beta into 3 of tx plus ty plus tz. If you add all these things, you will be getting the equation 4, as we have neglected the higher powers of alpha and beta. So using tx, ty, tz is equal to t. Since the dimensions, the stress is one unity, so tx is equal to ty is equal to tz is equal to t. We are taking all the three directions, the same stress has been applied. So final volume of the cube, that is equation 4, reduces to 1 plus alpha minus 2 beta into 3t. This is equation number 5. Now what is the final equation? The same equation 5 I have written once again to have a continuity. So final volume, increase in volume is nothing but final volume minus initial volume. What is the final volume? It is nothing but equation 5, and initial volume is nothing but we have taken in the initial conditions, it is 1. Initial volume is 1. So increase in volume is final volume minus initial volume. We are getting as 3t into alpha minus 2 beta. Let that be equation 6. We know that volume strain is nothing but the ratio of change in volume to the original volume. Change in volume is nothing but the equation 6, that is 3t into alpha minus 2 beta, and the original volume is 1. So in volume strain is nothing but equation 7. So we know that bulk modulus K is equal to, as per the definition, force per unit area is nothing but longitudinal change in change in length by original length, that is longitudinal strain. We know that K is equal to T by 3T into alpha minus 2 beta. As per the definition of the bulk modulus, it is nothing but compressive stress by compressive strain, that is T by 3T into alpha minus 2 beta, which is nothing but 1 by 3 into alpha minus 2 beta, as TT gets cancelled. So here we are getting the bulk modulus in terms of alpha and beta, that is 1 by 3 into alpha minus 2 beta. In the previous sessions, we have seen this relationship between y, k and n. Now here we are seeing the relation between bulk modulus, alpha and beta. Next we see the expression for rigidity modulus eta in terms of alpha and beta. Consider a cube of dimension L. A, P, S, D be one of its faces with side ds. ds is the side which is fixed. Let the tangential stress T applied along the upper force. As a result, cube deforms to A dash, B dash, S and D. As S and D is fixed, A reaches to A dash, B reaches to P dash, and the diagonal DP has come to DP dash. Now PP dash is taken as X. You can see in that smaller diagram where PP dash is taken as X. Now here let alpha and beta be the longitudinal and lateral strain coefficients produced along the DP per unit stress when stress applied T along AP. Now if you look at the figure here, angle of shear theta is nothing but PP dash by L, that is X by L. So angle of strain is nothing but theta, which is PP dash by L, X by L. We are going to use these equations in the next slide. Now extension produced for a length dp due to tensile strength is T into dp into alpha, as we know that X is equal to T alpha into L. Extension produced for length dp due to compressive strength is T into dp into beta, which is equation 2. So the total extension along the length dp is T into dp into alpha plus beta. From the figure, total extension dp is approximated to px dash. As px is drawn perpendicular to dp dash, therefore equation 3 can be written as px dash is equal to t dp into alpha plus beta. From the diagram, you can say that dp is equal to L root 2. Also, P dash x is nothing but Pp dash cos of Pp dash x. Since it is an isosceles triangle, theta is very much less and approximated to 45 degrees. Pp dash can be taken as cos 45 degrees when we know that cos 45 is 1 by root 2. So P dash x is equal to Pp dash by root 2, that is x by root 2. That is what is been given over here. Now substitute equation 5, 6 in equation 4. We get x by root 2 is equal to t into L root 2 alpha plus beta. Rearranging the terms, x by 2L is equal to t into alpha plus beta, because theta is equal to x by L. Therefore, x by L can be taken as theta is equal to t into alpha plus beta, which implies 1 by 2 into alpha plus beta is equal to t by theta. They're just rearranging the terms, bring theta to denominator. You'll be getting as t by theta. We know that t by theta is nothing but eta. Therefore, hence rigidity modulus eta is equal to 1 by 2 into alpha plus beta. Thank you.